All right, ladies and gentlemen, our afternoon session begins. Among the efforts helped that the Welfare and Safety of the Racehorse Summit has helped launch is the Racing Services Testing Laboratory, which has performed tests on samples from more than 80 surfaces. Executive Director is Dr. Mick Peterson, who has become probably about as well known as anybody in the industry, and for all the right reasons. He has been helpful to so many racetracks. I've been privileged to be the moderator for some of the racetrack superintendents' field days, and it's really interesting to see how well they accept what he does, how anxious they are to work with him, and how he's been able to help so many tracks. He'll be giving us presentation first. He is the Executive Director of the Racing Surfaces Testing Laboratory and the Libra Foundation Professor at the College of Engineering at the University of Maine. He will be followed by Glen Kozak, who has worked with Dr. Peterson and who has been very innovative. He's an example of seeking more information, taking on innovative practices. You just imagine what it's like to be running the New York Racing Association racing facilities. You think of the 3 tracks, but there's more than 3. They've got turf courses, dirt courses, training tracks. He's got that all under his wing, and it goes through quite a number of various climatic situations during the year. So I'm looking forward to this, and I'll turn this over now to Dr. Mick Peterson.
Thank you, and it's a pleasure to be here. As you heard, the Racing Surfaces Testing Laboratory is an outgrowth of this Welfare and Safety Summit, so I feel like this is, for a lot of these ideas and concepts, this is really coming home. I'm going to start out specifically not talking about racetrack surfaces, and a lot of you have already seen this. And the thing to keep in mind is when we look at catastrophic injury is multifactorial. There's conformation, there's shoeing, there's training, there's track surfaces. In fact, I even came into this doing work with Dr. McElraith and some of his colleagues at Colorado State working on training. So I'm going to start and end by reminding you that the tracks don't cause the problem, but they can improve the situation. So there's nothing in this industry that has to do with the health and safety of the horse and rider that we don't need to be focused on. But we can't be blinded by any one aspect of the problem. Well, why do research on surfaces? There's some well-developed work on biomechanics. It started out pretty early with Muybridge. Probably some of the first biomechanics work ever done was done with a galloping horse. There was a fundamental issue with work that was done on racing surfaces in that it was usually done with a regional focus. And I don't know if you've looked around the United States, but there are some dramatic differences in climate and materials around this country, as well as even training practices. And so when I came into this whole game, it was looking at the dramatic changes. I was in Colorado at that point, and now I'm in Maine. And so I had no regional focus. And so at that point, it was time to look at this on a broader perspective. We're now looking at it on an international perspective, and the story just gets more interesting. We need standard testing, but we have to focus on the horse. The testing needs to be based on the biomechanics. So I'm going to start out reminding you what the track has to do for the horse. First thing that happens during the critical stage of the interaction of the hoof and the track surface is the impact. This is when the hoof is coming down on the track. There's relatively low vertical loads, but the horse is moving along at a constant speed, but the hoof is stationary for a period of the time while it's in contact with the ground. So what happens is if the horse is going 35 miles an hour or 40 miles an hour, the hoof is going to have to go 70 miles an hour, then be completely stopped, then go 70 miles an hour. There's some dramatic changes that are happening during that deceleration of the hoof on the surface. What we have is during this phase, this initial impact when the hoof is first contacting the racing surface, we need to be able to have a soft surface but we need to have a surface that will allow a little bit of give, that will allow the hoof to slide slightly. That reduces the peak accelerations in the fore and aft. I simplified the injury statistics, or the injury interpretation, because I'm an engineer. But if we look at this and we put too high a load on there, we get chips, we get fractures. As the horse is propelling themselves forward, though, there are different needs, because at that point you don't want the slippery surface, you don't want this surface to give underneath the hoof, you want it to support the forward propulsion of the hoof. So you want this shear string. So basically think about this. You need a surface where the hoof can come in and slide, slow down, stop, but then continues to support the horse as the horse is propelling itself forward. Again, simple interpretation of injuries, low shear strength, you get bowed tendons. All right, so what this really means is, if we think about this, it doesn't matter whether it's a fracture, a chip, or a bowed tendon, it's still career ending for the horse and represents a risk to the rider. So at that point, we can't just make it harder or make it softer. We've got to make it, well, just right. So what the rider feels is the performance. We can't neglect the performance. That's also what the bettor's looking at, is the performance in times. If we look at musculoskeletal loading, we're looking at safety. Working with a group of researchers from the UK, Sweden, New Zealand, and the US, we came up with a list of 5 functional properties. The idea of this is to get away from using engineering words all the time and think about this from the rider's perspective, from the trainer's perspective. Then as we go forward, we can begin to include more measurements to understand the horse's demands on the surface. The words we came up with are not perfect, but they're workable. If we look at it as firmness, cushioning, responsiveness, grip, and uniformity, the next step we have is, then can we measure those parameters? Let's look at what those parameters mean. And think in terms of focus on safety. This is horse and rider we're going to focus on. We want consistency. Firmness is that initial give. That's initial, when the hoof is first contacting the surface, it's that deceleration. You feel a little bit of shock if it's too hard. Cushioning seems similar, but you think about that. That's after you've begun to put the load, the weight of the horse is transferred forward. So there's really an initial firmness, then there's the cushioning that occurs as the horse is transferring the load forward. Responsiveness is kind of confusing unless you think about it in terms of, this is actually a picture from an arena. But if you look at that surface underneath, you can see the entire arena is giving. See the bounce the entire surface gives. This is the energy return. Trainers are often talks about a responsive surface or an energy return. That's the bounce. It could be hard on the top. It could not have that initial cushioning, but it could still have the energy return. Grip, that's really thinking about turns, thinking about that initial, that being able to propel the horse forward during the propulsion stage. And finally, uniformity. Uniformity is when we start talking about safety and we start talking about Wolff's Law, as we heard about yesterday. This is really the go-to issue, because it really affects firmness, cushioning, responsiveness, and grip. And what we really want is we want the entire surface to be the same from stride to stride and from day to day. Consistency is perfection, and that's what we're looking for. Okay, if we look at the surface during the gait, then again to review, firmness, cushioning, responsiveness, grip, and then the uniformity, which is really going back to those first 4 measurements. Now, how do we measure these parameters? We have to start with the horse. If we're going to make engineering measurements, we can't start with soil engineering, we can't start with particle size, we have to start with the horse. Initially, this work was funded from the AQHA Racing. It started in 2001. We had a prototype machine in 2004. So we're at a decade now. And if we look at what we have to measure these complicated materials. The track is also difficult because it's nonlinear. The more load you put on it, the stiffer it is. It's also strain rate dependent, meaning the faster you load it, the harder it is. So in this case, the synthetic material shows creep deformation. So if you sit on there for a long period of time, it'll continue to sink. Dirt and turf have this dynamic response that are very moisture dependent. So what we've got is we've got a lot of terms in here, so the only way we can do this is to measure it like we would use an actual horse. The problem is horses have good days and bad days, so we need the mechanical horse. I'm repeatedly asked, is there a small portable instrument that we could use to measure the turf on a day-to-day basis? If we can come up with a small portable horse that's interesting to watch race, we'll be fine. At this point, we don't have a small portable racehorse, so we do not have a small portable instrument. But I'll come back to this. There's some workarounds. This is sort of an inside joke, but it's the biomechanical surface tester. Orono is referenced. There's also a Berlin artificial athlete, and Orono is where I live, and it is a very small, inconsequential place, and Berlin is much more consequential. So this was a joke that my colleague in England decided to call it the Orono biomechanical surface tester. But all right, this is the machine. It started the discussion in 1998. We've now got 60 tracks, 8 synthetic tracks, 5 turf tracks. We can do the testing in 40 minutes. That's between training and racing. We do a standard of 24 locations. On the right, you see the video of the hoof impacting the surface, and this is the machine. There's 2 axes, so it strikes and it slides forward. You can see the dirt moving there. All right. It's got some legs, as it were. There's now 4 machines in the US and Europe. There's one at the Swedish University of Agriculture. There's one at the California Horse Racing Board. And in the UK, there's the Races, which is a consultancy that's formed from 3 different universities. We're pretty close to the start of a standard international method. Now, the bad news is this big machine. You can see it's mounted on the back of a tractor. It's mounted on the back of a van in either California or Sweden. It's also being used in places other than horse racing. During the Olympics, there were 2 of the machines used at Greenwich Park. So we've moved beyond the initial idea of using this for racing. But again, a show jumper is big and heavy, and there cannot be a small portable device for measuring show jumping arenas. So what do we have? The data. We've got 6,000 tests over a decade for 80 racing and training surfaces with this machine. What you're looking at there is the slide. There's a huge amount of discussion on slide, on synthetic versus dirt. We have a much smaller data set for turf, but if we look just at the dirt and the synthetic, this is almost 3,000 measurements on dirt and synthetic. What you see there then is, the first thing you notice is, these are statistical outliers. Why do we care about the statistical outliers? Well, it might be machine malfunction. But you know, it's just as likely that that is actually the proverbial bad step. We may have actually, with those 6,000 measurements, found some scattered bad steps. Why does that work in terms of what Dr. Bramlich was talking about, is an overloading event after accumulated microdamage is what's going to lead to that bad step. That doesn't mean that there wasn't pre-existing musculoskeletal disease, but what it does suggest is that one more step isn't going to go well. But here's another lesson that we get out of this. The range of the slide on dirt is much larger than synthetic, but some dirt surfaces have less slide or higher grip than synthetic. There's a story here about dirt that becomes really important. What it's really saying is, if you look at these two, if you look at the upper bound and the lower bound on the synthetic, you notice something really stands out. The variability is dramatically lower. So there's something different about synthetic surfaces that means the variability is lower than dirt. This is the cushioning, the vertical direction. Same sort of a thing, we look at the outliers. But if we look at this, again, even the softness. So saying synthetic is softer than dirt is, yes, on average it is. It also varies a lot less. And if we think about uniformity, we think about risk to the horse, we may care so much more about uniformity than we care about the absolute values. The horse has some ability to adapt to a surface by altering the gait, altering the length of the gait, altering the center of the mass of the horse. But if we start talking about variability on a trip around the track, or variability between tracks, there's a lot lower ability to adapt. And remember, when we're putting the horse at risk, we're putting the rider at risk. So the important conclusion, the take-home message on this is dirt is more variable than synthetic. I want to show you one other tool that we've used, and this is more perspective on this. As soon as we started seeing variation in the tracks, immediately we started asking how we could reduce the variability. Oak Tree Foundation funded the purchase of a ground-penetrating radar that we've used. This allows us to image the cushion. We can look at the cushion depth, we can look at the harrow depth, and we can basically see problems before they get to be any real issue. It's also kind of neat because we also can make moisture content really stand out. So this is actually ground-penetrating radar data that was taken on Oak's Day. It's just a matter of windowing the electromagnetic signal to get the moisture instead of the cushion depth. And this is what it looks like. Around the inside there, you can see a red area. What that means is it's drier. Around the outside, you see it's actually quite consistent, but it's wetter. But you might remember what happens when you ride on the rail there. All right? It's a drying track. So there may be that there's something there that represents a performance difference on the track as well as a consistency issue. Okay, so I've talked about a decade of testing with the biomechanical surface tester. For the synthetic tracks, we've got spatial and temporal, day-to-day and around the track variability. For dirt and turf tracks, we've got spatial and temporal variability. Synthetic tracks, I'm not going to spend a lot of time on that, but the maintenance is huge. Absolutely needs to be consistent. And there's segregation of the material. Wherever you work it, it'll separate out. Dirt and turf tracks, though, we see one dominant feature. There's a lot of discussion of the type of material. The material has to be consistent around the track. But water completely dominates the equation. Water is the big issue that you'll see day to day and around the track that'll vary. Yes, maintenance matters. This is a dirt track. This was done on a dirt surface. This is the rip and till that's used on some of the tracks. If we look at it, it starts out kind of hard. This is the vertical direction. This is the horizontal direction. And it's got a little bit of slide to it. What happens is, if you dig it down, it's got a little less slide because the hoof is penetrating down into the surface further, so it's grabbing the hoof, so it's not sliding as far, and it's a lot softer. What else do you notice, though? This is the range. It became a lot more variable. This is the issue we're always dealing with maintenance of the tracks. This is why there's a whole bunch of different equipment that Glen's going to talk to you about. It's managing that variability and managing the response. It's also not simple. I mentioned the regional variation in this. There are 3 different dirt track designs. The hoof contacts the surface during impact. During breakover, it toes down, it goes into the surface. And then, like I mentioned, it has to be able to support it during that entire process. But keep in mind, there's 3 different designs. So, the other question I get asked is, can we tell them how to maintain it? Well, probably not, because a lot of these methods have evolved for local material and local climate. So we've used X-ray diffraction. That was a method that hadn't been used prior to the development of the Racing Surfaces Lab. And we assumed that the design and maintenance is defined by rainfall and materials. So the assumption, our presumption getting into this was that the people who've been taking care of these tracks for decades probably knew something we didn't know. Well, it turns out they do, in fact, know something we didn't know coming into this as academics. We've got the 3 different designs. They have different clay content, which were statistically significant. They added organic to the high clay content tracks, and the annual precipitation was also statistically significant. Meaning, what do? If you don't have very much rainfall, you have more clay, you add a little organic to hold the moisture, and you got a good track. If you have a lot more rainfall, you certainly don't put any organic in it. You can use sand because you want it to drain quickly, and you don't need the clay in there because what you're doing is the moisture is holding your track together. So the maintenance has to match the materials. What about the safety of the horse and rider? is one of these surfaces less safe than the other? Using data from the equine injury database, we can't find any statistical significance in the difference between the three track designs. So what we're really saying is that looking at these different designs, they've evolved for the local climate. There's not a difference in safety between the three different designs. And also, the other key lesson is next year may not be the same as this year. So we may have evolved for a certain climate. If we have a dry year or a wet year, it's going to be a very different animal out there. The other thing is, if you sort this out, the best dirt is not as good as synthetic, but it's close. If we look year-to-year variation, even with the large year-to-year variation in dirt tracks, the good dirt tracks are almost as good as the synthetics. All right, in my role, I have to just accept the synthetics for what they are and what's happening. As we go forward, our path forward has to be what is happening that's different with the best dirt tracks, how can we replicate that, and how can we create the safest surface for every horse and rider out there, given that they will be dirt surfaces. And what we really need to do is see what causes the variation from year to year, and also see what's the difference between the good, best dirt tracks and the other dirt tracks. The dominant feature on this is water. You're going to get tired of this. I'm sorry, but water completely dominates this issue. Synthetic tracks are insensitive to moisture. They're hydrophobic. You coat them with wax to keep the water out of them. This is from Derby week. What's happened? It rains. Look at the peak load. Shear strength doesn't matter that much because of the design of the track, but it's softer because it's wet. No surprise there. We get the same effect in the lab. If we change it from 8% to 10% to 12% to 14% moisture content, the shear strength varies dramatically. That shear strength is basically the loading of the soil underneath the hoof. So what happens? Add water. And this is hard because it gets faster than slower with more water, but it all makes sense. Now, synthetic tracks change too. You all have seen this, you've seen it, some of the handicappers even paid attention to it. And it turns out that on a synthetic track, there is no better indicator right now of the speed of that track than the temperature. You can use a Clegg hammer, you can use a going stick, you can use a penetrometer, any of those handheld devices, none of them predict the speed of the horse better than the temperature of the surface. And it turns out that if you're at 4-inch depth, it's pretty good too. Well, if you look at the Arlington polycapping site, you can get that 4-inch depth, and a few people have used it. But here's the key with a synthetic track. You couldn't keep the two ends of it at a different temperature even if you wanted to. You couldn't get a 10 or 15 degree temperature difference between one end of the track. You'll get some shadowing, admittedly. It'll make a small temperature difference, but it's a consistent temperature. Remember that consistency with a synthetic track? But a dirt track isn't that way. You can have dramatic differences in moisture content around a dirt track. So we're seeing more and more as we move forward on the dirt tracks. What are we going to do to make them better? It's going to be water. That's the gap between dirt and synthetic. It's got to be water. So the major message from the research end of this is maintenance, especially water, needs to be controlled. There's different maintenance for different materials. You water, harrow, you add material, you grade, and there's a million details. They all matter. How do we fix this? Now, I've already told you that I don't want to tell the superintendents how to maintain the track. They may be using 3 or 4 generations of knowledge at that particular track with some of that same material in order to develop the techniques, and if I walk in there and tell them how to change it, it's probably not going to turn out well. But the whole ISO, International Standards Organization, that we heard about like in laboratory accreditation, the idea is not to tell anyone how to do the test, it's to ask them to document what they're doing. What is going to be done? What has been done, and how did you verify the work? And then you have to close the loop when you're done with that. Checklist manifesto. I was out there in the back. That's the philosophy, though. It's really keeping track of what you're doing. It's an aircraft checklist. You know, when you do aircraft maintenance, if any of you got a pilot license, you know there's a checklist you go through. That same checklist is the same sort of a checklist that needs to be part and parcel of every time you climb onto a tractor in the morning, a checklist and documentation of everything that was done that day. Why, again, to belabor a point, if we look at dirt tracks, the injury on dirt tracks vary between years. Now, dirt tracks don't have new staff every year. They don't have new material. They don't have new methods. They do things quite consistently. So it almost has to be weather. If you have a track that goes from here to here to here, or jumps around like some of these do, it almost has to be weather. If we look at synthetics, for the most part, it's quite consistent from year to year. Again, consistency. What does that mean? Temperature is going to be more consistent from year to year than moisture. Okay, so how do we understand and control the track variation? We've got the Orono biomechanical surface tester. With the surface tester, we're making measurements. We know water is the single biggest input variable in the turf or the dirt. And then we know the proper maintenance. If we talk turf, it's the same as dirt. It's aeration, top dressing, and verticutting. So it's a series of steps that are taken every day, every week, every year, depending on what's doing it. And again, we're going to copy. We are not going to innovate on this. The idea is to use best practices. If we look at aircraft maintenance, again, it's what's going to be done, what has been done, and then how the work is verified. Just like you would in surgery. Same people, weather could vary, we have to respond to the weather, but we're going to document processes. So what you're looking at there is why Glen Kozak is up here with me. This is the next stage of racing. What's happening there is the iPad is in the lab of the track at the racetrack. The data is being entered in real time. Not defining what's done, but keeping complete focus on what the process is. One of the previous welfare and safety summits formed the Racing Surfaces Testing Laboratory. The last one had one of the goals was establish daily reporting of maintenance on racetracks. This gives you an idea of where we're at this point. These are the tracks that are at some level of participation. At this point, the information is in the gathering stage. As you know from the equine injury database, we're talking years to pull together enough data to be able to make any conclusions or to share anything. This is the weather data from Arlington Park, which is like what you saw from Woodbine. It's done in 15-minute intervals. And this is the Keeneland maintenance data from one day of the maintenance, and this was on the synthetic track. So at this point, we have manual maintenance systems at 8 racetracks, automatic tracking at 6 racetracks, and weather data at 12 racetracks. Weather, I've already mentioned. It needs to be a standard weather station at a standard location. The quarter pole at Woodbine, the quarter pole at Arlington. If you look around the racetracks, we're gradually getting to the point where we know more or less that we're going to know what the horse is seeing in those critical areas. From the jockey injury database, you saw the locations we should be paying attention to. It's the final turn, the stretch. Starting gate 2, but the final turn and the stretch. That's when we need to absolutely control as well as we can. Also, an evaporation model. For turf, this is quite well established. Manually entering the data for the track maintenance, and I'll go through this quickly, but these are the screens we're using. Glenn will tell you what's going into these screens, but you can see, look at the large number of lines in there for the maintenance. There's a lot of steps to this. This isn't simple. And there's a separate form for training every day. And then my favorite, the form for the water truck use. Number of loads, direction, speed, and then you can go back and get historical data. Moisture content. Again, I'll mention moisture content. This is about a $1,200 device. It's used to map moisture content. It then can automatically download into the maintenance quality system the data, then they're placed on a map. The other thing that's done is cushion depth maps from probing. Most tracks are doing this manually when they do it, but this is something that has value as well to the handicappers potentially. And then this is the automated system where there's GPS equipment on the water trucks, the tractors, and all the equipment that goes out there. This doesn't replace the manual entry of data. What it does is it's the cross-check. The data gets better going into the manual system, and mistakes are avoided. So every day, every trip that the tractor takes, there is a corresponding line on here that shows speed and position on the track. The next step, and this is what Santa Anita has supported, is the development of a water depth measurement in the truck. What this means is we'll know how much water was put on the track. So the sensors are placed on here. We know the depth of the water. We combine this with the GPS. We suddenly know how much water was put on the track. One more step, this is where Keeneland has contributed, is to develop an evaporation model. Evaporation models are used extensively in crops. They're evapotranspiration models where they include the transpiration from the leaves of the turf or the crop. However, we do something rather abusive to our fields, is that we will harrow them 17 times a day. So the evaporation model still needs to be developed. This is a part of what's going to happen for the first race meet on dirt at Keeneland, is the evaporation model. Keep in mind, what are we focused on? The largest variables. We control the variables on the dirt. We control the differences from day to day and around the track. How to inspect the work then? We have to say what's going to be done, what has been done, and how work is verified. The surface tester then becomes something that's only used at the start of the meet and on the big days. The portable inspection tools that exist are things like the Clegg hammer. Now the Clegg hammer is used by some people, but it does not correlate to race times. And unless we're racing 2.25 kilogram horses, it doesn't correlate to the biomechanics. The going stick is much more promising. It has some link to biomechanics. It's good on the turf because it assumes a depth of the turf. The penetrometer, which some of you may be familiar with, is used extensively in France and in Australia. It's the most well-established, but it's the relationship to winning times is not a particularly strong predictor. So we've got some tools. None of them are perfect. None of them are correlated to injury. And for example, synthetic track temperature, as I mentioned, is more strongly correlated to race times than any of these measurement devices. So there's no simple tools. Using the Orono biomechanical surface tester on a periodic basis. Remember, there's multiple machines in the US and two in Europe, 2 in North America. And we understand the variables. Then we control the variables that are critical. And to make turf and dirt more consistent, we control the water. You can see on this, that's Ascot, Arlington Park with the going stick, and then this is Naira and Santa Anita with the TDR. As we move forward with these then, this data also is mapped and goes directly into the database. So what are we doing? We're pulling the information together. We're pulling the information together in a way that we can compare day to day, we can compare to outcomes. And then the maintenance quality system is the combined database. The goal is to improve what is going to be done, what has been done, what is verified. Then we look at the outcomes. Injuries to jockeys and horses, effectiveness of maintenance methods, and even expenditures, because there are some unnecessary expenditures. But the critical issue then is, using the maintenance quality system, what is the rider's response? And most importantly, what is the risk to the rider and risk to the horse? The epidemiology, thanks to some support from Bill Kasner, the Racing Surfaces Testing Laboratory has already moved forward on bringing all of our data together with the equine injury database to begin to assess the risks on the data we have. And that'll be an ongoing project. Okay, I told you I'd repeat this. In racing, no disease, no breakdown. That's again my simplified version of it. But the issues in musculoskeletal disease, while they include surfaces, they include a lot of other factors. But surfaces and vet checks and some of the things we've discussed today, those affect every horse on the track on a particular day. So as far as an industry focus, those are the things where we know that we can improve the industry by looking at these risk assessments and looking at track conditions. The other lesson out of this is, sometime when you look at the industry, you don't see this level of cooperation, but there's nothing proprietary about safer surfaces. The Safety from Start to Finish initiative from Churchill Downs was absolutely essential to the start of this development of this. As Santa Anita changed out and they were looking at a slower, safer surface after they transitioned to dirt, they contributed the money for the water truck, sand durability studies. New York, the maintenance quality system, that electronic database, that came out of the governor's task force. Now Keeneland, with a new dirt track, the evaporation model and X-ray diffraction of candidate sand. This is all going back to the industry. Nothing's proprietary on this. All of this is being returned to the industry. So Keeneland has benefited from Santa Anita's sand durability. That's a part of the design of the track is Santa Anita. NYRA's maintenance quality system will be a part of Keeneland's next step forward. Keeneland is now moving the ball down the field. And as with everything else in horse racing, it took a lot of people to contribute to keep it moving forward financially. And also, needless to say, you look at the quantity of work. This is the last summer's staff at the Racing Surfaces Testing Laboratory in Orono. Now I'm going to pass this off. None of this works. It's all just an idea unless there's implementation. And for those of you who don't know Glen Kozak, I related the story about, this was quite a few years ago when I first interacted with Glen, and when he responded on his BlackBerry, like instantly to my, when BlackBerries were still a thing, I knew that we had a somewhat different track person at New York. So he looks at his phone and he's moving this forward.